All right, continuing on. So fire response. There's a discussion here that revolves mostly around this idea of the emergency management continuum, which you'll be able to see on my poster here is an evolving matrix of variables that include the values at risk, your resources available, time is a very valuable resource, the values of the resources under threat, and the short and long-term goals of the management scenario. And the evolution of this continuum usually trends towards resource protection, and especially in the fire industry or fire, realm, there's the glorified Hollywood at all costs emergency response that people seem to expect, but may not be the best case scenario, and it might put the first responders at risk. But when we're trying to keep things under control, it usually benefits us to be proactive and to set ourselves up for success. But how to do that is a very complex question, as a problem like erosion control eventually points to our social concept of an emergency. Erosion is a very slow process, but can have dramatic effects, much like the slow accumulation of fuel in a forest can have a dramatic effect of a severe forest fire. Our response to both those situations is different than if we'd been more proactive earlier on. Changing these outcomes requires delineation of variables we can control and those that we can't. So it turns into more of a risk assessment. My engineering brain sees erosion control as a simple study. You could find a certain variable, governing variable, everything's physical, but when you start relying on predictive services for, say, precipitation events that may lead to erosion on such and such slope of such and such angle on such and such aspect with such and such burn severity due to such and such fuels loading, well, you start adding a confidence interval, and then predictive services tend to not have as finite an answer as other civil engineering problems tend to. Then you throw in the subjective and relative idea of value at risk. If there's $1 million home on one side, if there's a community that has already experienced severe natural disaster and wants a full suppression strategy versus a fire use strategy, a community that could benefit from a prescribed fire but hasn't had that happen, and now there's a severe fire, well, you start relying more on social expectations than actual valid scientific fact. And again, this gets back to that 75th anniversary of Smokey the Bear. Fuel loading in our forest today due to Smokey is greater than ever and has been shown to lead to more frequent and severe wildfires. And returning to a natural burn cycle in all parts of the country, it's getting done much better now in the southeast and the southwest, but we require more public cognizance. As familiar as the public is with Smokey, we need to recognize the value of fire in our woodlands today. How do we do that? Well, the risk assessment of where we're at is a complex question. There's several key elements to fire. The basic fire triangle is heat, fuel, and oxygen. But for a wildfire, you already have the fire ignited. So you have fuel, you have conditions favorable to combustion, and the conditions favorable for spread of that fire. So usually in any part of the United States, these conditions are only met a few days each year. You would hear of these as those red flag warning days of low relative humidity, high temperature, low fuel moisture, and sometimes high wind. Alignment of a fire with topography is hugely important. Natural fires tend to be lightning strikes which occur at the top of ridges where there's usually not much fuel, but human-caused fires tend to occur down the bottom of drainages where there's a lot of fuel, and fire likes to run uphill better than it does downhill, so that's where we find these extremely large fires. Myself, as a smoke jumper, in the future, this summer, will be going to fires usually caused by lightning that are usually on a ridgetop and usually in some area that nobody would otherwise go to because you can't drive to it, so we have to fly to it and fall out of the sky to it. But in terms of actual fire spread and risk to humans, usually this is around population centers. So alignment topography is super important. Dense fuel loading. People like to live near dense forests. They think it's nice and quaint, but this is also increases their risk of fire effects. And when there is dense fuel loading, the fires tend to burn more severely, which increases the effects or the potential for erosion for a single given precipitation event. Fire is a nexus of variables of varying return intervals. So how to define all these variables and when they line up to give, say, a heat map of fire risk is a difficult process. But we have several publicly available models out there. I'll put the links in this folder. They'll be under the cited materials folder. But we have fire behavior and spread models, and these use anywhere from, I believe it's 6 to 42 different fuel definitions, and each of these inputs occurs at a different resolution based on certain flights and publicly available data over the West. Usually it's specific to the Rocky Mountain West. But we have fuel loading on 1 kilometer, 400 meter, and then in some cases 10 meter resolution. This is either by color, just basic variance in reflectivity, but it gives us the ability to define high fuel, high risk environments that have high risk of large fire spread should a fire occur there. And that allows the local agency to design fuels treatments, fire breaks, and any sort of other mitigation techniques to prevent large fire spread, especially towards population centers. Other fire models include Behave Plus, Landfire, Farsight, and FlamMap. And as you can see on the poster, the bottom of that first page, these all lead to our predictive services capabilities.